Imagine looking at a massive grid. Can you determine if the total number of squares inside is odd or even without actually doing the multiplication? Look at a 3 by 3 grid. 9 squares leave 1 over. Odd parity. A 3 by 4 grid pairs perfectly for an even total. This proves the rule. Grids with an even side have an even area, while odd by odd remains odd. By checking the parity of the dimensions, you can identify the parity of the total area instantly, skipping the need for complex calculations. Algebra works the same way. Take the expression 3n plus 4. We can determine if this result is always even, always odd, or if it changes based on the input. Let's test it. If n is 3, the result is 13, which is odd. But if n is 8, the result is 28, which is even. When n is 10, the result is 34, even again. The parity of the output shifts depending on the input. This shift happens because the multiplier, 3, is odd. An odd multiplier preserves the parity of whatever number you plug in, causing the final answer to toggle. However, some expressions are consistent. In 100p, the multiplier is even. Since any number multiplied by an even number results in pairs, the output remains even for any whole number. In 2n plus 1, we take an even multiple and add 1, which means the result will always be odd. We can use these consistent patterns to find the exact value of any number in a sequence, no matter how far down the line it is. Look at the even sequence. At position 1, the value is 2. At position 2, it's 4. At position 3, it's 6. Each value is exactly double its position number, which is why the formula for the nth even number is 2n. Now look at the odd sequence directly below it. At every position, the odd number is exactly 1 less than the even number above it. Knowing that the even number at position 100 is 2 times 100, can you figure out what the 100th odd number would be? The 100th even number is 200. Subtract 1, and we find that the 100th odd number is 199. This gives us our general formula. The nth odd number is always 2n minus 1. This relationship allows you to pinpoint any odd number instantly by simply finding its even counterpart and moving back by 1. Let's test these rules with a logic puzzle. Lakpa has 3 piles of coins and calculates a total of 205 rupees. Let's see if that's actually possible. Lakpa has an odd count of 1 rupee coins and an odd count of 5 rupee coins. Since an odd count times an odd value is always odd, both of these piles have an odd total value. The third pile has an even count of 10 rupee coins. Because at least one of those numbers is even, the value of this pile must be even. When we add them together, the 2 odd piles combine to make an even sum. Adding that to our third even pile means the final total must be even. Lakpa's total of 205 is odd, which is mathematically impossible. By identifying the parity of each part of the problem, we can find errors in the total without ever needing to know the exact number of coins. You've now mastered grid parity, algebraic consistency, and the sequence formulas for even and odd numbers. Here is your final challenge. First, use the 2n minus 1 formula to find the 75th odd number. Second, determine if the expression 6j minus 4 will always be even or odd for any whole number j. Solve the formulas, explain your reasoning in the comments, and subscribe to Textbook Toonz for episode 3, where we dive into magic squares.